Now in this section we want to look at Stokes' theorem. Stokes' theorem is going to be a three-dimensional version of the circulation form of Green's theorem. Now Green's theorem actually has two pieces. It has a circulation piece, which is what we're going to look at in this section, and it had a flux piece, which we're going to look at in the next section. Now Green's theorem tackles both circulation and flux. Because it's in two dimensions, it's relatively easy, and we were able to find that the circulation, which is what this is circulation. So give it a gamma right here, is equal to this integral, which is the integral on the circuit curve C. It's a closed curve and you're moving in a counterclockwise motion, of the vector field times the tangent vector ds for some arc length. And then we learned that that is equal to the double integral over the region of the curl of f, right? And this is the curl. Curl is g sub x minus f sub y. That's curl. All right, what was it measuring? Well, you have some closed curve and you're moving in a counterclockwise motion around the curve. And what you find is that how much the vector field that this curve is sitting in, how much it helps push along that curve is what you are finding. So this is the curve C and this is the region R that you're integrating over. All right, so now let's extend this to three dimensions, and that's Stokes' theorem. So we have some vector field, now it's three-dimensional vector field, FGH, and we have a surface that is in three space. It's bounded by a closed curve, and we're going to assume counterclockwise motion along that curve. This would be equal to the circulation, which is, again, the same line integral along the closed curve circuit for the vector field times the tangent vectors, which is the curl, right? So the surface integral for the curl dot product with the normal vector. Now, which normal vector is this? It's the upward normal. So let me make a note. N is the gradient of W, where W equals z minus z of xy. So this is the level surface, and we're pointing in the upwards direction. So n is in the upwards direction, right? Because the z is positive. So when we take the gradient, the z component will be 1. That's just standard issue for how these how this theorem works. All right, so we're moving in a counterclockwise direction, and then of course to do the surface integral, the double integral over the surface, the way we actually do that is the double integral over the region of the gradient, the del operator, cross product with the vector field, right? That's how you find your curl, times n dA. Remember that this piece right here, which is this piece right here, is the curl. We went over how to do that in a previous section. All right, so here's a drawing of what's happening. So you can see you have this curve down below, right? It's kind of coming around. That's your curve. That's C, and it has a counterclockwise motion. So what you're determining is how much the vector field is helping, and the normal vector is sticking out, how much of that vector field is helping that circulation, right? Helping that move around the edge of that surface, right? So this is the edge of the surface. It forms a curve. That's what it means when it says it's bounded by that curve, right? So you have the edge of the surface, it's bounded by that curve, it's forming that curve, and so we're determining, or Stokes' theorem determines, the circulation along that curve based on this vector field and this surface. So Stokes' theorem is finding how much that vector field is pushing along that boundary curve. Another advantage of Stokes' theorem, for the record, is that it can transform from a line integral to a surface integral or vice versa. So sometimes one of these is easier than the other, and sometimes you want to transform from this version over to that version, or from this version back to this version, or whatever. And so because they're all equal, you can do so. Now let's put this into practice. So we are going to find the circulation for the vector field F, which is negative y, negative x minus z, y minus x, on the path C, which is the slanted ellipse that forms the boundary of the part of the plane z equals 6 minus y that lies inside the cylinder x squared plus y squared equals 16. So you might be thinking, what in the world, what does that look like? Well, x squared plus y squared equals 16 is a cylinder. So let's look at that. So that's a cylinder. And then you're cutting into it with a plane, z equals 6 minus y, which is this diagonal plane inside there. And if you have to stay inside the cylinder, but you're cutting at a diagonal, it's going to form an ellipse right there. So that's what we have. So we have an ellipse inside the cylinder. So now we have to draw that. So I'm going to start by drawing a cylinder as best I can. So I'm just going to draw it above the x-axis, or excuse me, above the xy plane. That's what I meant. Above the xy plane. So it's right here. So we've got the cylinder, I've got the z-axis sticking up right here, I've got the y, and I've got the x. All right, so then it kind of comes down low and then goes back up. So the best way to do that, I think, is just going to be to kind of draw it like this. We know it's not perfect because it's on an angle, but there we have it. All right, and we're particularly interested in that circuit that's going around, right? That's what we're interested in, traveling counterclockwise. So think about it. If this is the xy plane, then we're going this way along it. Like that. Okay, so first thing we're going to do, we're going to do this twice, but we're going to use the parameterization method. So we're going to use a line integral, aka parameterization. The old school way of doing this. All right, so we need an equation for our ellipse, for that circuit around the ellipse, as a matter of fact. So R of t is equal to, well, it's an ellipse, right? So we have to think about the x, the y, and the z. Okay, so remember that this ellipse is packed inside this cylinder, right? So the x and the y, if you look straight down, the x and the y are pretty easy to figure out, right? Because they got to be inside that cylinder, and the cylinder is radius 4. Okay, so that means that the x and the y are going to be dictated by that. What gives it the elliptical shape is actually the fact that it's tilted. So let me write that over here real quick. So packed in cylinder. So ellipse packed in cylinder. And the cylinder is radius 4, right? Because it was x squared plus y squared equals 16. Actually, I just realized, why bother writing it over here? I should just write it right here. So the ellipse is packed in that cylinder. All right, so therefore, I know that the x is going to be 4 cosine of t, and the y is going to be 4 sine of t, because I'm moving in the counterclockwise direction. But what about the z component? What about that third component? Well, remember that for the ellipse, z equals 6 minus y, right here. But we know that y is 4 sine t, right? Because this is x right here, this is y right here. Then for the z, it was 6 minus y, but we can't do that, right? We're going to have to switch it over. And so we're going to write 6 take away 4 sine t. There is our R of t. All right, now we're going to need our prime. Because that's how we're going to find this integral. All right, so our prime would be the derivative of sine, or excuse me, derivative of cosine is negative sine. Derivative of sine is cosine. And the derivative of sine is cosine. And the derivative of 6 is 0. So this is going to be negative 4 cosine t. All right, now let's figure out our vector field. So the vector field was negative y, negative x minus z, y minus x. But that's not useful to us because we need to have the new version. So it's negative 4 sine t, negative x is 4 cosine t, so that's negative 4 cosine of t, minus z. So that's minus 6 minus 4 sine t. And then y minus z, so that's 4 sine t minus 6 minus 4 sine t. We are going to simplify that. All right, so that makes negative 4 sine t. This is negative 4 cosine t plus 4 sine t. So 4 sine t minus 4 cosine t minus 6. And then this is 4 sine t plus another 4 sine t. Oops, I messed up. This is not y minus z. It was y minus x. I'm so sorry. Okay, so this is y. So 4 sine t minus x. X was 4 cosine t. So that's 4 sine t minus 4 cosine t. Sorry about that. All right. Now, where are we going with this? Well, there's circulation. There's a by hand formula that we learned long time ago in section 17.2 when we first learned the parameterization method. So we want to take circulation is the integral over the curve, so the line integral of f dot t ds, which is the integral from a to b of f dot r of t, or prime of t, excuse me, dt. So let me write those formulas in. And it just occurred to me I should have labeled these. This was step 1. We were parameterizing our curve, and this is step 2. We found our vector field and the appropriate terms that we needed, and now we're doing step 3. We're finding the circulation. So this is step 3. All right, so we are going to take the integral. Oh, we needed to have our r of t needs to have domain, but it's rather obviously 2 pi, right? Because we're making one circuit around. So we're going to go from 0 to 2 pi. And then f, which was, when I figured it out correctly, negative 4 sine t, 4 sine t minus 4 cosine t minus 6. And then 4 sine t minus 4 cosine t. And we're going to dot product that with our r prime, which was negative 4 sine t, 4 cosine t, negative 4 cosine t. I can just fit this in dt. All right, so let's start multiplying. 0 to 2 pi. So negative 4 sine times negative 4 sine is 16 sine squared t plus, all right, 4 sine t minus 4 cosine t minus 6, all times 4 cosine t. So 4 times 4 makes 16 sine t cosine t minus 16 cosine squared t minus 24 cosine of t. I'm multiplying each term in here times 4 cosine t. And then I'm going to do it again over here. Minus 16 sine t cosine t. And then plus 16 cosine squared t dt. Now, it looks pretty terrible. However, there's some things going on. So we have a minus 16 cosine squared and a plus 16 cosine squared. So those are gone. We have a 16 sine cosine and a minus 16 cosine. So those are gone. And so that means that we're finding the integral from 0 to 2 pi of 16 sine squared t minus 24 cosine of t. And this is what computers are for. Right? We will make a computer find that for us. By the way, I also wanted to double check my dot product just to make sure because that's a lot of multiplication and a lot of terms. So I typed in my vector field and I typed in my parameterization and then I said, hey, find me that dot product and simplify it, and sure enough it did, and I did do it correctly. And then I integrated that from 0 to 2 pi and I come up with 16 pi. Lovely. Okay, so this is 16 pi. Now we need to do it all again using Stokes' theorem, but we'll do that in the next video.